Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. We've seen in this playlist that the Serre duality theorem is a powerful tool to control higher cohomology. In this video, I want to tell you about the Serre duality theorem in arbitrary dimensions. And just as in the case for curves, we will need to use a special canonical sheaf that's associated to the projective variety in question. And to compute that, I also want to talk about a very useful adjunction formula to help us make that computation. Okay, so what's the setting that I want to have a look at today? So we'll work out some algebraically closed field K, and we're going to consider some projective variety of dimension D. And it has to be nice in a certain way. Certainly smooth would be nice enough, but we can be a little bit more general. We can be something called a cohomology. So don't worry too much about what that means. I will give you some extra examples of things which are smooth, which are not smooth rather, but are still cohomology a little bit later. Okay, so let's see what the Serre duality theorem tells us, okay? So it involves something called a dualizing sheaf. That's why it's named dualizing sheaf is suggested because that's the one that's used in the Serre duality theorem. And that's going to be denoted omega x. And this is the same symbol as the canonical sheaf because in the smooth case they will be identified. So this is a coherent sheaf and it has this very, very simple property, okay? So what's that simple property? It's the following. For any coherent sheaf F here, you can compare firstly, you look at this cohomology group, h to the d minus I of this F. That's some finite dimensional vector space over K, and you look at the dual of that. That's going to be isomorphic to this vector space here, this x vector space, the xi of F into omega x. Okay, so let's note a couple of things here. So firstly, on this side, okay, this is in the contravariant variable, so this is a contravariant functor. The cohomology is a covariant functor, but when you dualize this here, then you get a contravariant functor as well. So that's the first point. The second point is that the sum of the two indices here, and this is where the duality comes in, is the dimension of the variety D. So in the Serre duality theorem that I gave for curves, what we did was we saw that if you look at H1, so D equals 1 here, if you look at H1 of a coherent sheaf and you take the vector space dual, you get the HOMS, which is x0 of that sheaf into the canonical sheaf. Okay, so this generalizes what we saw for curves, okay, where D equals 1, and well, the interesting case there was I equals 0, but it also works for I equals 1, and in fact they're the same, really the same theorem. Okay. So that's the Serre duality theorem, and it's extremely useful because it allows us to control this cohomology. And in particular, if you look at HD, right, HD, that's the case where I equals 0, that is computed by some x0, which is a HOM. And it's a lot easier to compute HOMs and to make that vanish than to look directly at this. Okay, so that's one of the reasons why we look at that. And we'll see an example of how it's useful in a little while. Okay, so what are ways to compute this omega x? So here's an adjunction formula. So what is this omega x? So firstly, as I stated before, when x is smooth, omega x is just the canonical sheaf. So in other words, you take this cotangent bundle, okay, so that's going to be a rank D vector bundle since it's dimension D, and you just look at the highest exterior product of that, so it's now a line bundle, so it's an invertible sheaf, okay. More generally, how you can apply the Serre duality theorem is if you have any irreducible divisor y inside x. Now this y inside x might not be smooth, but if you have a divisor, okay, so here it's x is smooth, so this would be a Cartier divisor, okay, then this y will turn out to be cohomology. And not only is it cohomology, but we can really say what is this dualizing sheaf. So in this case here, we can't use this definition here, okay, it's not so well defined, the cotangent bundle, but we can get it from omega x as follows, okay. So what we do is you start with the dualizing sheaf on x, so this is more true more generally, by the way, if x is cohomology itself, okay, and this is a Cartier divisor. And what we do is we take that invertible sheaf on x and we tensor it with this invertible sheaf on x, which is O twisted by y. Okay, so that's some invertible sheaf on the big X, And then we restrict that down to y. If you like, you tensor that with the structure sheaf on y, okay? So you mod out by the ideal sheaf on y. This is a little bit long, so we'll often abbreviate it to omega x. You twist it by y, and then you restrict it to y like that. Okay, so let's have a look at an example of each of these. Okay, so the first one is something that we've seen before. It's the adjunction formula for plane curves. Okay, so let's suppose you have a degree d curve y inside P2, so it's a plane curve. Okay, so what's omega P2? I'll tell you the answer for this, but we kind of saw what it was when we computed via check cohomology, the cohomology for P2. So this is going to be O minus 3. Okay, so remember when we have P1, it was O minus 2. For P2, it will be O minus 3. P3 will be O minus 4, and so forth. OY here, so we want to take that omega of the ambient P2, and we want to tensor it with this twist by this degree D curve, OY. And since it's the degree D curve, this is isomorphic to OD. So the tensor product of these two is just OD minus 3, and to get omega y, we have to take that tensor product and restrict it to y. So we restrict OD minus 3 to y. Okay, and that is our canonical sheaf. That's quite nice, right? You have some degree D curve here, and all you have to do is to look at OD minus 3. That's D minus 3 times the multiple of some hyperplane H, if you like, and you just restrict that to y. Okay, and that will tell you exactly what this is. That's rather nice. So let's have a look at the degree of this. So if you want to compute, for example, what is the genus of this? Of course, the best way is to look at the degree of omega y. That will tell you the genus. And this formula gives it to you very quickly, because the degree of something like this, when it's written like that, is you just take the intersection product of y with this the corresponding divisor, which is d minus 3h. So it's d minus 3h dotted with y, and y, of course, is just d times h, or linear equivalent to d times h. So by Bezout's theorem, this is just d times d minus 3. And that's the adjunction formula that we saw for plane curves earlier in this playlist. So that's rather nice that this formula here nicely encapsulates that in a nice simple way. Okay, so what's a very important use for this Serre duality theorem? So as I mentioned before, for curves, we use this to control cohomology. Okay, so one of the things that we often want to do is we want higher order cohomology to vanish. Okay. And so I want to show you an example of how that works. So suppose now you have y inside P3 is going to be a divisor, which is a degree D surface. Okay, so what happens in this case, if you have a degree D surface, then what's omega y? We can use this formula again. So you need omega of ambient P3. So that's going to be O minus 4. And then you have to twist that with OY. So this is degree D. So you have OY D minus 4. That's what that is. Okay, and one of the things that I want to show is that let's suppose you look at this OY, and we're going to twist it. So this is inside P3, so we can twist it by n times a hyperplane section. And one of the things that you should expect, or one thing actually that we've seen with Serre vanishing, is for n large enough, right? The higher cohomology, so H1, H2, and so forth. Okay, so in this case, this is only a surface. It's H1 and H2 there, the ones that might potentially be non-zero. For n large enough, this will be 0. But do you have an actual effective value of n where you can say that it will be 0? Well, Serre duality gives you such an effective bound. Okay, so I claim that when n is greater than 4, d minus 4 rather, n is greater than d minus 4, you'll have this. Okay, so let's just see how that works. So suppose n is greater than d minus 4. Then what happens? Okay, so what I want to do is I want to write this H2 as an X2. So it's normally X2 of O into OYN. I've written this down as OY, X2 of OY d minus 4 minus n into this omega y. So remember, if you tensor with an aligned bundle, okay, that's a Morita equivalence of the category, so it doesn't change the x. So this OY is OD minus 4, so you can cancel the OD minus 4. So this is really X2 of O minus n to O, which is the same as X2 of O into ON. So that's the same as this H2 here. Okay, once you have it in this form, you can use the Serre duality as I've written it here. Here's the omega y. So what you just do is you just look at this term here and look at, in this case, the dimension is 2. I equals 2, so this will be h0, h0 of O d minus 4 minus n, and it's a star of that. And since n here, you're subtracting n from this d minus 4, and n is bigger than d minus 4, this is going to be a negative number. And so since that's a negative number, of course, the h0 of this is going to be 0. Okay, so this is a way to get an effective bound for when this actually is 0. Okay, so this is good for showing that h2 is 0 for n greater than d minus 4. One thing that's a little bit unfortunate for surfaces is that we don't have so much control over the h1, because when we look at h1, that's written in terms of an x1 for a surface. Okay, so even if we shift this around to make it an h1, it's telling you some h1 is isomorphic to another h1. Okay, so it's a bit less useful, but nevertheless, you use it quite a lot still for surfaces. Okay, so I'm going to finish off this video just by giving you some of the main ideas for how you prove the Serre duality theorem, to try to demystify it a little bit, and in particular demystify this adjunction formula. Okay, so I don't expect you all to understand the details. This is just a bit of evidence for why it's true, so that you can see that actually it's not such a curious thing after all. Okay, so let's see. So the first thing, actually, it turns out that for Serre duality, the key case is to do the case where I equals d or 0. They're kind of dual, so it's not a big deal which one that we do. So let's look at the case where I equals 0. So you want to look at hd star is isomorphic to hom into this omega x. Okay, so you can think of this first statement in a couple of different ways. One of the ways you can think of it is, well, let's look at this hd and this this cohomology group. Okay, so this is a functor, it's a covariant functor here, and you look at its deal. So it's going to be some contravariant functor on this side here. So one of the things that you might ask is, can you represent this contravariant functor? And one of the things, this is the first part of the Serre duality, is saying that this is actually a representable functor. You can represent it by homing it into omega x. That's what it means to be a representable functor. Can you write this functor as hom into something inside that category? Okay, and we're looking at the category of coherent sheaves on x. Okay, so that's the first thing that's true. The second thing that's true that's rather interesting here is that, why is this a key? Why do you just want to do the case where I equals 0 and then you can work the rest of your way up? Well, it turns out that you can do this by induction. Why is that? Well, let's have a look at this. So this is a left exact functor as well. And it's it can be continued into an exact sequence by looking at x. Okay, so in the language of homological algebra, if your homological algebra is good, you have a connected sequence of delta functors. Okay, so that's what you have there. And what about on the right-hand side? Well, this hd, remember you have grothendieck vanishing, so hd plus 1 is equal to 0. So that means that this hd is right exact. Okay, it's a right exact covariant functor. And then when you put the star on it, it becomes a left exact contravariant functor. So these are both left exact contravariant functors. And so the point is that if you want to just say essentially that if both of these vanish so basically what you want to say is that since they're the same, you can actually show, and this requires a little bit of work, that the corresponding derived functors are going to be also isomorphic. What are the derived functors? So basically you can continue this into a connected sequence of delta functions. So why is that? Because, well, you've got a long exact sequence in cohomology, and when you dualize that, you'll get something that goes in the opposite direction. Okay, so that means that you can continue this with hd minus 1 star, and then continue that with hd minus 2 star, and so forth. Okay, and that's the key for showing this. So this particular isomorphism we've already seen in the case x equals Pn, and using that argument I suggest that this gives you actually Serre duality for Pn. So this is the usual way you prove Serre duality. You prove it for projective space first, because it is something about projective schemes. Okay, so you prove it for projective space first. And then what you do is that you bootstrap from that. You say, well, if you can prove Serre duality in certain varieties, you can prove it for other varieties. And then since you have it already for Pn, okay, that's one. everything you can get from Pn, and so you get your answer. So in particular, the key point is that suppose you have a finite map from y to x, and y is Cohn-Macaulay, and x you have Serre duality for, so it's Cohn-Macaulay, okay? So the first thing to note is that, well, in this case of this finite map, if you have a sheaf on this y, this coherent sheaf on y, you can push it forward to a coherent sheaf on x, okay? So if this is actually an embedding, which will be the key case to look at, okay, this is essentially the same sheaf, but it's just supported on that x, that y rather. So off y, in the open set, which is the complement of y inside x, x minus y, is going to be 0. And then on y, okay, it's going to be given by that f. So what I want to show that is that in this sort of case, you have an adjunction formula. So Serre duality on x gives Serre duality on y. So I want to sort of indicate why that's true. So suppose you have Serre duality for x, so you know that this is true for x. Then you want to show that then you can prove it also for y. So if you change this to y, and this to omega y here, okay, and then since you've changed it to y, the dimension also goes down by 1, okay, you get the same thing. Now on this side, on the cohomology side, right, changing from x to y really doesn't do anything except for there's a shift in the index here, which we can also push over to the other side. Okay, there's a shift. So this remains the same. So what you want to basically say is that when you go from x to y, there's also no change on this side except for the shift in the index. That's all we need to do, okay? So we're going to do that. Yeah, so this is, so the shift in the index, it will depend on, of course, what the dimension of y is inside here. Okay, so if they're the same dimension, actually, there won't be anything. So you can also use it even if you have a finite map of smooth surface to smooth surfaces. Okay, that's one case to apply this sort of idea. But I want to just apply it in the single case, the single case of a divisor. Okay, so y is a divisor inside x. And that's going to give us our adjunction formula. So the last thing I want to do in this video is to show this basic idea. How does this work? So this is part of the proof of the Serre duality. Okay, I want to show you how it works in the special case where this finite map is just the inclusion of an irreducible divisor y, Cartier divisor, inside this x. Okay, and it's also going to give us this adjunction formula. Okay, so how's that going to work? Let me show you. Okay, so we're going to take that divisor, Cartier divisor y inside x, and what are we going to do with that? So the first thing is I'm going to rewrite this adjunction formula. This is going to be the thing which I claim gives me my Serre duality. This is the thing that, okay, so if I put in this for omega y, okay, I get essentially this, the same thing as what I have here, except for with an index change. And the index change, since I've got a divisor, it means that it's going to be off by 1. Okay, so the first thing is that I'm going to rewrite this in a funny way. I'm going to write this as something called an x sheaf. Okay, so what is this x sheaf? Okay, so first thing is that you can talk about Hom sheaves, remember? Okay, so if you've got two coherent sheaves here, okay, what is this? So coherent sheaves just means essentially on each affine open set you have modules. Okay, so to work out what this coherent sheaf is, you just have to know what is it on those affine open patches. So on each affine open patch, what you can do is you can look at these two modules. They're OX modules, right? So OY, this is a quotient ring of this OX, okay, on any affine patch, okay? So this is a quotient ring, so it's also a module of OX, and this is of course also an OX module, okay? So we're looking on each patch. So you can compute X as modules. So that's, and you do that on each and every affine open. Since localization commutes with this X formation of X, you get a sheaf out of this, and this will give you a coherent sheaf known as this X here. Okay, so that's the first thing that you have, this X sheaf. Okay, so we're going to rewrite this as an X sheaf. Okay, which basically means on each affine open set, you just compute the X groups. Okay. Okay, so why do we do that? Because once we have this formula written down, we can just perform the magic of homological algebra to show that, well, if f is actually a coherent sheaf on y, okay, on this divisor, then think of it as a coherent sheaf on x, so looking at I lower star f more technically. If you want to compute this x of I lower star f into omega x, what you can do is you can compute this as an x in y, okay, it's x I minus 1 y of f into this x here. So if you happen to know about change of rings and spectral sequences, this is exactly what's going on. The sum here, I minus 1 and 1, gives you this I number here, and that's kind of what's happening. And this x is this sheaf x that I mentioned here. Okay. So this is kind of advanced stuff, but it's kind of good to just see how homological algebra can just be used and pulled to come up with such a wonderful theorem as this one here. So part A is quite easy to see why that's true. Okay, so what we'll do is that we'll look at the following short exact sequence which defines the structure sheaf on Y. OX maps to OY, so this is a quotient ring or sheaf of quotient rings of OX. Okay, and basically you just mod out by the sheaf of regular functions which vanish along Y. So OX minus Y, the ideal sheaf of Y. Okay, so we're going to do two things to that. We're going to compute two things which will help us identify these two sides. Okay, the first thing is that you can hom this whole thing into omega x. Okay, so we're going to hom it into omega x, and it will turn out that omega x, and normally it will be like an invertible sheaf. It won't be in general, so even here it won't be in, so if x is smooth, it will turn out that it's an invertible sheaf. And also in this particular case here, it will be, as you can see, an invertible sheaf because it's a restriction of an invertible sheaf. But in general, if you have x's just cohomology, it won't be an invertible sheaf necessarily. Okay, so that suggests to you that when you try to hom OY into omega x, you don't get anything, and that's the case. Okay, so now we can hom OX into omega y, and we want to do the sheaf hom. Okay, so of course, if you just hom on each affine open set, this is just the ring itself, so you just recover this omega x. And then you do the sheaf hom of this into omega x, so you get omega x twisted by y. Okay, so I guess you can see that by using the tensoring by y, and that's an equivalence. Okay, and then the next term will be x of this into omega x, and that's what you see here. And the next term here, well, remember, you're doing the x to over OX. So this is free, okay, and hence projective on any affine open. So it's going to be 0 on all those patches. So when you do the next term, the next x1 term is actually 0. So you get this exact sequence. So this will identify this x sheaf with essentially the coconal of this map from omega x to omega xy. So the other thing that you can do to the sequence is you can tensor with omega xy. So what you get here, of course, when you tensor with OX, okay, that's just gives you back omega xy. When you tensor with O minus y, the minus y cancels the y, so you get omega x. So you also get this when you tensor with omega xy. And the last thing is that when you tensor with OY over OX, you just restrict to y. So that's what you get on this side, okay, is when you tensor that. So the coconal of this map can be identified with both this and with this x sheaf here. And that's how you get part A. And the second part is hard to prove, and it depends on how much homological algebra you know. If you happen to know some, hopefully this will tell you what's going on, and if not, this material is fairly standard and you can find it in a lot of places. So the way we're going to do this is we're going to compute these x groups using injective resolutions. So the way you should kind of think of an injective resolution is essentially on each affine open, okay, you're going to get an injective module. Okay. So this omega x, you can replace it with an injective resolution like you see here. And now what we're going to do is we're going to kind of use this injective resolution of this omega x to compute this X sheaf. So we're going to basically, this is the injective resolution on each affine open patch. So we can do this on each affine open patch. Okay, so that's what we will do. And what do you see? So firstly, we can use this injective resolution to compute what this is. And we can also use, since this is computed locally, okay, we can also use a projective resolution of OY. And what's a projective resolution of OY? Well, here's a projective resolution of OY. Okay, and it's only got two terms here, OX and OX minus Y, and these are, remember this is invertible sheaf, so it's locally free, so on each affine open, or if you go to sufficiently fine affine opens, it will be free. Okay, so we can use this, and that tells you that there's only going to be x0 and x1. And as I've kind of mentioned before, you can't map OY into omega x because this is kind of torsion free. Okay, nothing is going to be supported just on Y. Okay, so the only term you have here is x1. So that's the first thing that's the only thing that you have. Okay, so one thing we can do is when we compute this this x, okay, so we can hom this OY into this sequence, and kind of the point is that the only cohomology that you pick up is this X sheaf here. Okay, so that's what happens. Okay, so you do hom OY into this sequence, so there's a sheaf hom OY into I0, that's going to be 0 anyway. Okay, then you have the sheaf hom of OY into I1, that's this term here, and the sheaf hom of OY into I2, and so forth. Okay, so the first one is 0, so there's the shift, that's going to be the shift that's involved here. And what is the cohomology of that sequence when you just look at that? Well, you just get this one here because we computed this X the other way. Okay, so that's this X shift. So that's the first thing, is that we have this exact sequence that you see here. Okay, that gives us essentially a type of resolution of this X1 sheaf of OY into omega X. And the other thing that's rather interesting is that, and this is something that if your homological algebra is good, you'll see, and follows from the adjoint associativity. Okay, so the fact that tensor and hom are adjoint functors, is that since OY is a module over OX, okay, so you've got a quotient ring here. It turns out that when you hom this OY into this injective, that this will now, it's an OY module and it's an injective OY module. Okay, if you do it on each affine patch. So on each affine patch, this will be an injective OY module, and hence this is an injective resolution of this sheaf. Okay, so now remember what we're trying to do here. Okay, we've said that we're assuming that Serre duality holds on X, so we have something like that. And what we're going to do is now we're going to say that, well, this same isomorphism will give us the isomorphism that we need on Y. So why is that? Well, when we change X to Y, basically nothing changes here. This is the same, except for there's a change in the index. This goes to D minus 1, but we'll flip it over so it's D minus 1 minus I. So we'll change this to I plus 1 over here. So we want to change the index by 1. And then what happens here is that when we change the omega X to omega Y, the omega Y that we're going to use is this one here. Okay, so that's what we're going to show. So remember, what we're trying to show is basically we're saying that this is the same, okay, and we're assuming that we have this. So we just have to show that it's the same when we swap from this to the omega Y, where this is omega Y, and there's a shift in the index I. Okay, that's what we need to show. So why are these why are the two X's the same when you use X and when you use Y? Okay, so let's compute using injective resolution of omega X first. So what do? We just hom F into this. Okay, you're just homming F into this. So you're looking at maps from F into all these IJs. Okay, and then you take the cohomology of those hom groups. Okay, but what do you note? So it turns out that, let's have a look a bit closer at all these hom sheaves. Well, what are these hom sheaves? So basically you're looking at So if you had an OX here, this will be all of I1. So basically, hom of OY into this is just all the sections of this which are annihilated by the ideal sheaf O minus Y. So you're just looking at the sections of this module, okay, so on each affine piece, sections of this module which are annihilated by O minus Y. Right? But since F is actually a coherent sheaf on Y, it's annihilated by O minus Y, if you think of it as a sheaf on X, okay? It's annihilated by O minus Y. So when it maps into any of these IJs, it has to map into the bit which is annihilated by O minus Y, and that's precisely these sheaves here. This sheaf here is basically all the sections of IJ which are annihilated by O minus Y, so that you get a hom from OY into IJ, in fact. So in other words, if you map F into this injective resolution, okay, that's the same as mapping F into this injective resolution here, because this is a all of these sheaves here are just subsheaves of the things here, and F mapping into these, because F is annihilated by that O minus Y, that ideal sheaf has to sit inside this subsheaf. So you might as well map it into here. So it doesn't matter whether you use this one or this one, and you'll get the same cohomology. And so that means that it's the same on this left-hand side. Doesn't matter whether you use omega x or for omega y you use this. And where does the change in the index come in? Well, note that what you've had here is that here you start from I0 and go to I1 and so forth. But here, remember that term dropped out, and you're starting from I1 going to I2 and so forth. And that allows us to prove simultaneously the junction formula. And this type of idea, more generally, is how you prove the Serre duality theorem in general. I hope you enjoyed this adventure in pure mathematics.